Okay, so today we have a smaller number of people. I don't know why, but anyway, so let's start. Okay, so I guess in the last lecture, we start to talk about ideal solution, right? So the whole point here is that we want to introduce as a first model to understand how we can apply all of the cool stuff we mentioned about thermodynamics, including entropy, enthalpy, and free energy. How can we use these quantities to understand the thermodynamic stability of the system, right? And we have been looking at examples of pure substance like water and ice, but as the focus is more on the material aspect, and we know that we're dealing for materials, typically we're dealing with alloys of different types. So it's necessary for us to look at how we could apply these things to understand alloy, right? Even it's a simple model, but at least we need to do this. So that's what we start and what we left over. So for the alloy system, we're still interested in phase transformations, but as we showed in the ice and water example, right, to understand the phase transformation, the first thing we need to do is to understand the thermodynamic stability of two candidate phases, right? So for the case of ice and water, we have liquid versus solid. So these are two thermodynamic states. We compare their stability for given condition or given pressure, right? And then we can say at this temperature, it will have a transformation because, for example, ice is more stable below the melting point. That is the way how we approach this. And the quantity we use to compare or to access the thermodynamic stability is the so-called free energy that we talk about, right? Now, in the case of alloy, we basically going to do the same practice, right? But the difference is that the two states we're comparing are different, right? In the case of ice and water, we just have pure liquid and pure solid. But in this case, we have two different solid state. One we call solid solution, which is kind of a homogeneous mixing of two or more different type of atoms. But in this binary solution case, we just talk about two type of atoms and mixed in a homogeneous way at atomic level. This is what we call solid solution. We also refer to this as a mixing state, right? And the other state or other phase that we talk about is the so-called demixing state, which corresponds to the extreme case that we just have a portion of the system is pure A and the other portion is pure B, right? You just literally take a portion of A and a portion of B and put them together, and you form a phase separate state. So these are the two states, or the two so-called phase, if you want, that we want to compare, right? And we know that to understand which one is more stable, we have to look at their Gibbs free energy, right? And in the last lecture, we showed that it's very easy to write down the Gibbs free energy for this demixing state. We call this state 1. Right, so this is easier, and this is a state 2. So the Gibbs free energy for this particular state, which we denoted by G1, is simply the molar fraction of A times the molar free energy of A plus the molar fraction B times the molar free energy of B, right? This is very easy to understand because if you have 1 mole of pure A, right, and your free energy is going to be Ga, but now it's only a fraction of that. So this is your total free energy contribution from this portion, right? For the same reason, Xb times Gb is your contribution of the Gibbs free energy for this portion. And the reason why we can write down this is because we ignore the energy associated with this interface, because this is a macroscopic system, right? So interface contribution compared to the bulk, to the volume, is vanishing. So we can write down the Gibbs free energy only consider the contribution from the bulk. That's for G1, quite clear, right? And for simplicity, because eventually we're going to compare G2 with respect to G1. So we'll just write down G2 with reference to G1 or with respect to G1 as G1 plus delta G mix. I heard someone that you have to mute your speaker or your microphone. Thank you. That's much better. Yes. So that's for the free energy for the G2, right? So as you can see in this formulation, the key is the so-called delta G mix. That's going to measure the difference of free energy between the two different states, 1 and 2, right? And we also briefly mentioned that, the value of delta G mix or the sign of delta G mix is going to determine which one is going to be stable, right? If delta G mix is greater than 0, this means which phase is more stable. G1 is more stable, right? Because G2 is higher than G1, right? And for the same reason, is delta G mix is smaller than 0. This means that my G2, this mixing state, is more stable. Of course, this delta G mix will depend on external conditions, depend on temperature, maybe pressure as well, right? But for any given set of thermodynamic conditions, you can definitely assign a value for this guy, and then you can basically tell at this condition which phase is more stable. So that's basically what we have described. Okay, so after this quick recap, let's move on. So because the whole point is that we want to compare the two states and find out which one is more stable. So, and inevitably, we're going to find out what is the expression for delta G mix, right? And for this particular system, we're going to dive into the mathematics and find out a very cool expression for this, which allows us to obtain a lot of insights. So now let's take a closer look at what is this delta G mix, right? So now we go back to our definition of free energy, right? We can always write the free energy in forms of the enthalpy contribution and the entropy contribution in this particular form, right? If you don't forget about this, go back to the previous lecture. Yeah, this is how we define the Gibbs free energy for a system that have fixed number of particles, pressure, and temperature, which is the normal condition that we have for most thermodynamic system. Okay, so we have a contribution from the enthalpy and the contribution from entropy. So for now, we compare the system at the same temperature. So T for the first state and the second state are the same, right? And they have different contribution from the enthalpy and entropy. So I denote these by 1 and 2, respectively represent the state 1 and state 2. And this is my state 1, and this is my state 2. Okay, so now literally we just take the difference between the two, right? And basically we take G2 minus G1, I got delta G mix. And when you take the minus between these two expressions, first you're gonna get H2 minus H1, right? We group these two together and call this the enthalpy of mixing, okay? And then we group the entropy term together, we call this the entropy of mixing, okay, for the same reason. And then the delta G mix can be written as this, okay? It can be written as the contribution from the enthalpy of mixing minus T times the contribution of the enthalpy of mixing, and then this is the entropy of mixing. Okay, so that's nothing new. We just use the definition for the free energy and write this in the form of mixing state, right? So we have an expression for delta G mix. So now what we define, how, we talk about, the topic will be ideal solution, how we define ideal solution. Now, once we have that, I can provide that definition. So for ideal solution, the enthalpy of mixing is always 0. Okay, so this defines an ideal solution. Okay, so which this means is that, it doesn't really matter how you mix this A and B or, black and white atoms, it doesn't really matter how they class together, you just mix them together and they do not care about their neighbors. Right. So basically, if I look at I'm a black particle, I do not care whether my neighbor is black and white, because that does not contribute to any difference in the interaction energy, right? So this is one particular, reason how you can have a delta G mix equals 0. This means that, the bending energy between any type of atoms in the system is identical. But we'll see that this is not the general condition, but this is one condition that very easy to understand how to achieve an ideal solution, right? So just the bending energy between black and white, white and black are all the same, right? But this is not the most general form, but let's just keep this picture for now, okay? So that's the enthalpy of mixing. Now, if we, plug this condition back into the free energy of mixing and setting the delta H mix equals to 0, the only term that left in the free energy of mixing, delta G mix, is going to be the contribution from the entropy of mixing, right? And then, of course, this is weighted by a minus temperature. But then this is going to be the key quantity that determine delta G mix, right? So that's basically, the key feature for a ideal solution, which means that the entropy of mixing plays a key role to determine the free energy of the system, or in particular, this is the free energy of mixing for the system. Okay, so that's what we're gonna spend most of time working on. Okay, so for now, the logic flow is that we want to compare the thermodynamics or the stability of the two states, and this amounts to compare delta G mix. And for ideal solution, we know delta G mix is directly determined by delta S mix, the entropy of mixing. So the next task for us is to find out an expression or model for this entropy of mixing for the ideal solution. Okay, so that's what we're going to do. Any questions up to this point? You have been very quiet today. Okay, if not, let's just go on. Okay, so now before we dive into this entropy of mixing, okay, I just want to say a few more words about entropy, right? So times. So basically, the best way, at least it seems to me that the best way to understand entropy is that you just look at the phase space. Single point can be represented as any single state of a system can be represented as a point in the phase space. Okay, so this is the previous picture that we introduced. Now, for those pictures, we're just focusing on either very schematic consideration or very simple system like a harmonic oscillator, right? But now we have a solid solution, which means that these particles, have a kind of fixed crystal structure, and all of the atoms are just doing some very funny vibrations around this state, right? Now, in this particular case, how we can further refine our definition of entropy or further understand, the contribution from each type of motion from the system. Because the whole point is that, if you look at the way how the system moves, right, it seems to be vibrating around a single point. So, this means that you can define a reference point and simplify the way how you define entropy, right? Because the vibrations are kind of, different from the contribution from that fixed point, which is a crystal structure. Okay, so this motivates us to think about, okay, whether I can reconsider the definition of entropy. So the idea is the following, right? So if we have a single configuration, this is going to be a single point, right, in the phase space. Now, if I consider that this is a, crystal structure at finite temperature, so everything is vibrating. Okay, I know you'll probably be laughing at this, but this is, the right way how the crystal structure vibrates. It's not like, each atom just doing individual vibration. They're doing this kind of collective or cooperative dancing. Okay, that's the phoneme modes. But anyway, so once the atoms start to vibrate, right, to form this collective modes, it's basically that you're exploring a slightly larger region, right, around the perfect crystal state, right? So suppose that everything is stopped vibrating, you cool the system to 0K, you're gonna have a perfect crystal, which is the red point I'm showing here, right? But once you increase temperature and everything starts to vibrate, you're exploring a slightly larger region around this point, okay, the center point. Does that make sense to everyone? I just want to make sure this is important. Okay, so now if this makes sense, then we can say, okay, the entropy or the number of states that contribute to the entropy is basically proportional to this volume of the region around the red dot, right? That is the states that can be accessed to this particular solid due to vibration around a crystal structure. Does this make sense? Okay, so entropy or the contribution to the entropy comes from basically all the states accessible to this particular solid material, and those states are associated with vibration of atoms around a fixed crystal structure. So it corresponds to a volume of, this small region centered at or around this red point. Okay, so that is for this particular picture. Now, if we think about this, right? So now, suppose instead of having just one fixed configuration, we know the solid, the different, if you have an alloy of two different type of atoms, there are many different ways that you can mix them together, right? And each of them will be a particular state or particular red dot around which the atoms can vibrate. Okay, that makes sense to everyone. So, if I'm showing that, okay, these are the different states of the system, but I'm just highlighting, the center point, all right? And then if I allow all of them to start vibrating, I'm sorry. So the, entropy associated with this whole system, okay, so now I'm talking a collection of all these states, right? Because in a thermodynamic system, all of these different type of disordered configuration can be accessible, right? And each type of this configuration, each particular configuration, gonna be associated with, a small region due to vibration, right? So now, if I'm talking about the entropy of the system, I need to collect all of these regions, right? collect their volume, and then that's gonna give me the total number of states available to this particular disordered mixing state. Does that make sense to everyone? Just to make sure that we're getting this picture. Okay, so now if that makes sense, then how can you write down the total number of states by collecting all of these regions? What is the best way to write down that number? Okay, so I have the answer for you. So again, if we use, this is a definition of Gilbert's entropy that we introduced a couple of lectures before, and omega is the number of states, right? And you can see here we write omega as the lowercase omega times m. Okay, so what is m? M I already introduced in the previous picture. Okay, so m is the number of states. I'm sorry. M is the number of states associated with the vibration around a single point. Okay, M, the capitalized M, is the number of states associated with the vibration around a single packing configuration or single atomic configuration, right? Now, if I have the total number of states for this picture, for this particular system, equals lowercase omega times m. Now I'm asking you, what is the lowercase omega? What is the meaning of this lowercase omega?
The microstate in one particular configuration.
The smaller omega is the total number of these configurations, right?
Oh, okay.
The capital M is the number of vibration, the contribution of the vibration coming from, for each state, right? So in here, like we only have a single state, right? And we know the contribution from vibration is M. Okay, we're using the same M for this picture. Here I have multiple configurations, right? And each configuration gonna be associated with M different states due to vibration. So if we have this small omega number of configurations, and each configuration have this number of states due to vibration. So I time omega times m simply equals to the total number of states accessible to my system, right? And this system includes a collection of different configurations, as well as the vibration around each configuration. Does that make sense to everyone? Just want to make sure that this is clear. Okay, if I got no answer, I assume this is clear. Okay, good. So the interesting thing that you see here is that, this way, this decomposition of the way how we count the states, right? By decomposing this into the vibration contribution and the actual number of configuration contribution, allow us to decompose, for some reason, to decompose the entropy also into two terms, right? Because we know this is natural log. So if we have a product within the natural log, we can take them out as two individual sums, right? So now if you see this term is what? Is simply the logarithm of the number of distinct atomic packings or distinct atomic configurations, right? And this contribution is from the vibration associated with each configuration. Okay, so basically now we define this part as the configurational entropy, and this part as the vibrational entropy for obvious reasons, because their contribution are from different sources, right? So for the configurational entropy, the contribution, or this omega is the number of distinct atomic configurations, or you can call it structures or packings, but they're the same thing, right? Distinct atomic configurations. And this vibrational entropy is due to the states associated with the vibration around a specific atomic configuration. Now, to write down this, we already assume that each of these atomic configurations have roughly the same number of vibrational states, so we can separate them. And this is okay if we're talking about the solid state, okay, at normal temperature, okay? So now if we write the entropy in this case, okay, so this means that at the same temperature, the vibrational entropy contribution are almost the same for different configurations or different phases, okay? So in this case, now if we go back to the definition of the entropy of mixing, we know that we have to compare the entropy of both the mixing state and the demixing state, right? And we need to make, make the contrast between the two. But we know that for both of these two states, the vibrational entropy gonna make the same contribution. So we'll take take one entropy subtract the other one, this vibration entropy cancel one another. So we don't have to explicitly consider this part anymore. Okay, so in our subsequent calculations or subsequent counting, I will say we just need to focus on the configurational entropy, because that's when you do the contrast, when you do the subtract from one to another, we compare two different states, the vibration entropy going to cancel one another because they have the exact same contribution. So the only thing that makes a difference comes from how many different configurations you can have associated with different thermodynamic conditions. Does that make sense to everyone? Okay, if no question, I assume this is good. So yes, so now go back to this, right? So we spent some time to describe this. Still we need to consider or keep in mind that when we talk about these solids, they're vibrating, but the vibration contribution for this state and this state, they're the same, so they cancel one another. So we don't have to really take into account. Now the only thing that we need to consider is the contribution to the entropy due to distinct atomic configurations or atomic packings, namely the small omega. Okay, does it make sense to everyone? Okay, so now here are some questions for you. I think I've been talking too much. I don't know whether I still have you with me or not. So I already give you the answer. Let me go back. So now if we look at this particular state, okay, how many distinct atomic packing configurations do I have here?
One.
One, right? That clear to everyone? Because there's no other way that you can group this. You can switch, probably you can put this part on this part, to this, but it's if you do a rotation, which is part of the crystal symmetry, get back to the same structure. So that one wouldn't be counting as a different configuration. So you only have one configuration, and we know as in those cases the entropy associated with this is 0, right? This is S1. S1 is 0. Does that make sense? Okay. So now we know that delta S equals to S2 minus S1. Now, if my S1 equals to 0, okay, so delta S mix, or the entropy of mixing, is basically the entropy associated with this particular state, right? So, and we know that, that entropy mainly contributed by the number of different ways how you can pack atom, under this particular condition or on this lattice, right? So the key, or equivalently, the entropy of mixing for the two system, or compare this to two state of the system, amounts to find out what is the number of different ways that you can pack these black and white atoms on this particular lattice. Does this make sense to everyone?
Yeah.
Yes, sir.
Okay, if no, yes, good. So this is much better than I expected. Okay, so good. So that's what we're gonna do, right? So that's gonna be the most juicy part for this class, for this particular lecture. Okay, so how are we gonna find out omega 2? Okay, yes. Okay, so now before we do that, I think there's a setup that I need to explicitly mention, right? So we compare the two states of the system, and for this state, basically we're just taking 1 mole of each, right? So we compare both of the state, and for this particular state, I'm going to give you XA mole of A, knowing that XA is smaller than 1, and XB mole of B, right? So that XA plus XB equals to 1. Okay, now for this particular mixing state, what is the molar fraction of A and what is the molar fraction of B?
0.5 and 0.5.
No, it's still XA and XB, right? We're comparing the two states at the same temperature, at the same molar fraction. Okay, so now if the reference state, if our state 1 has XA mole of A, XB mole of B, we're taking exactly the same amount of A and B, but preparing a solid solution. So for this guy, it appears to be that XA equals to XB equals to 0.5, but actually it's not, because if you count, I think you have more white than black, which is consistent with this. Okay, so I have XA mole of A and XB mole of B, and XA and XB are fraction because we're talking about 1 mole, right? Does that make sense to everyone? This is where we're gonna start from. Okay, so yes, so if we have that molar fraction, okay, yeah, it might be 60 over 40, but let's in general just consider these are number that we can specify later, right? Just say we have XA mole of A and XB mole of B, right? So now if I tell you that this is 1 mole of alloy, okay? And I just give you a number, say XA equals 0.6, XB equals 0.4. Can you tell me what is the number of A atoms and what is the number of B atoms in this solid solution state? If this is 1 mole of alloy.
Yeah, so if XA is 0.6, then there are probably 0.6 atoms per mole, like 0.6 atoms for just like, or maybe if you are considering the 1 mole of alloy, then you have to take the Avogadro's number of atoms of both the elements.
Yes. So this boils down to the question that, okay, I give you the molar fraction, right? I ask you what is the number of each type of atoms. So how can you convert the molar fraction to a number? You have to time, right? You have to time the total number of atoms in this particular system, right? But what is the total number of atoms? Well, I told you that this is 1 mole of alloy. So the whole alloy contains what one mole. 1 mole is, the Avogadro number, 6.02 times 10 to the 23rd, I guess, that number of atoms. So you can convert the molar fraction to an actual number, right? So in this case, if I give you the molar fraction and I tell you that I have 1 mole of the system, and you can easily compute what is the number of atoms for both A and B type. Did that make sense to everyone? Okay, I guess that is why it didn't work. Each time I think I go to, click some action and response to the Zoom, and then I have to go back to the PowerPoint to make sure that it can take my command. But anyway, so yes, so that's basically what I'm talking about. Okay, so if we have 1 mole solid solution, right, and we know that we have XA, which is a molar fraction of A atoms, we can easily compute the number of A atom, which is we call NA, and this is the number of A atom, and this XA is the molar fraction, and this NA is the Avogadro number. Okay, that makes sense to everyone? For the same reason, we can easily, whoops, I'm sorry for the confusion. This is supposed to be B. Okay, this is NB and this is XB. I'll correct that. Okay, this is NB and XB. But for the same reason, we can write down the number of B atoms. Okay, imagine these are B. Okay, not A. So we have number of A atoms and number of B atoms, right? And we have a total number of atoms, which is NA. And for simplicity, let's just call this N. Okay, so now here is your question. I have NA atom and I have NB atom, and altogether I have a total of NA different atom together. Now, now I begins to randomly assign an atom to each of this particular site. Okay, I can do this in the other way. I can do this in a random way, but for each site, I make sure there is an atom assigned and assigned according to the number of the atom in the system. Okay, so now the question for you is that how many different ways that I can pack this NA number of A atom and NB number of B atom on this lattice? How many different ways?
NA into
NA
NB?
plus NB factorial by NA factorial into NB factorial probability.
Oh, yeah.
Does this make sense to everyone? If I get no response, I assume this makes sense, and I will talk about the next stage. Do you want me to show you how this is the case, or?
Yes.
Okay.
Yes.
So let's forget about this. So let's talk about, okay, how many different ways you can assign A atom and B atom in the system, right? So let's forget about there are 2 different types. Let's think about, okay, how many different ways? Assume that each atom is different, right? Forget about only have 2 times. Suppose that we have a total of NA atom, and each of them are different, and there are NA available sites. How many different ways you can assign these NA different atoms into this different site? It's this factorial, right? Did this make sense?
Yes.
Okay. Because why? Because for the first site, how many choices do you have? How many different choices do you have?
One.
One.
You have NA, right? You can choose any one out of NA different atoms to put onto this particular first site. Oops, right? So for the first site, you have NA different choices. I'm sorry, we just, because I cannot show you on this blackboard. So let's just use n to denote the Avogadro number. So we do not confuse n smaller case a by n capital case A, right? Just call the number of Avogadro number to be n, right? To be capital N. So this is gonna hopefully remove confusion. So if I have n distinct type of atoms and I have n distinct sites for these atoms, and I claim that there are n factorial different ways that you can assign each atom to each site, right? And the reason is the following. So if I start with the first site, I have n different possible ways to choose an atom to put here, because we assume each atom is different, right? So we have n different ways, right? And for the second site, how many different ways, how many different choices do you have for this second site?
Would that be Na minus 1?
Yeah, it's going to be n minus 1, right? Because you already used one atom, so you only have n minus 1 atom to choose from. So your choice is going to be n minus 1, right? Now, what is the number for the third site? Naturally, n minus 2, right? Does that make sense to everyone? You see the pattern in here? So for each following, if you do this, and for each following site, you're going to have, 1 minus from the previous site. And if we go to the last, how many choices do you have? This is the last site. How many choices do you have?
Only one.
Only one, right? So, but if what is the total number of configurations? The total number of configurations is just to multiply all these different possibilities, right? For each side, you have different possibility, but it's a combinatorial. So you just need to multiply all these possibilities. And then we know for this side, you have n, and you times n minus 1 times n minus 2 times n minus whatever, all the way to 1. And what is that long expression for time all of these numbers together? It's a factorial. Does that make sense to everyone? So this is where you have the denominator, where the factorial come from. Okay, so now how we do have this denominator? Well, because we assume when we do this factorial, we assume that all the atoms are different, but it's not, right? The difference, the only two type of atoms. So after assign these configurations, I'm double counting, I'm not double counting, I'm over counting a lot of same configurations, because if you look at this particular configurations, all of these black atoms are the same, right? But when we do the factorial counting to get this numerator, we assume they're different. So we have to find a way to get rid of these overcounting. Does that make sense to everyone? Right. So if for a given configuration like this, how many more times I overcounted? Okay, the number of ways I overcounted this is amounts to that you flip all the black atoms, right? And you see how many different ways that you can randomly change all these black atoms, but still give you the same configuration. And that is given by Na factorial, right? Because you have Na number of black atoms, and for each particular packing configuration, if you switch any of these black atoms in any way, this won't change the final configuration. So you have to take out this number. And for the same reason, you have to take this overcounting due to the fact that all B atoms are the same, right? So that's why you get this. And then if you look at that, okay, look at this expression, okay, this is, if you go back to the combinatorial theory, okay, this is the combination, right? This is how, what is the number of ways that you can choose a combination of A and a combination of B. Okay, so that's exactly the same as we're showing here. But I think we already go through how we get expression. Are we clear on this? Okay, if you're not believing this, you can try it out for smaller configurations. A and B is small, but I'm telling you this is correct. Okay, so now let's move on, because now this is basically the key part. Once we understand, and the subsequent mathematics will just follow naturally. So this is omega. Why we want to count the omega is because we want to find out what is the entropy associated with this mixing state, right? So the next step is, yes, so this is what we already described. So the next step is to compute the entropy based on this omega, right? And how we do that, we just plug this into the the Gibbs entropy formula. And we see that we have a logarithm which is gonna act on this factorial. But nonetheless, we don't know how the logarithm acts on the factorial, but we know how the logarithm acts on division and production, right? So yeah, I already give you that. So, but the first thing we need to do is that we need to basically write this more explicitly. I can show you later. But before that, I want to introduce a important and very useful approximation called the Stirling's approximation that tells us how to deal with a factorial in a log. Okay, so this basically means that if you have a big number n here, very big number, okay, and I take the factorial of this big number, okay, and then I the whole thing is within the log. Okay, this can be approximate in the limit that n is large. Okay, can be approximate as n times log n minus n. Okay, so I wouldn't show this, but this can be easily shown from analysis. But anyway, so we just use this for the rest of the lecture, okay? And then using the Stirling's approximation, let's try to simplify what we have here, okay? And see whether we can get some more elegant expression. So as the first, I said, so now I'm just focused on the logarithm part, and we can use what we know to write down these three terms, okay? That makes sense, right? It's quite clear. And then we use the Stirling's approximation, right, to expand each of the factorial within the log in terms of this expression. Okay, so the expression I'm warning you going to be a little bit lengthy, but it's not difficult to work out. Okay, so don't worry if you do not follow exactly what I show you. You can always work out this later. So again, I'm using n to denote NA plus NB because it's more convenient for me to work like this in the beginning. We just plug in the Stirling's approximation, right? And this, this is going to be grouped as n. So you have n log n minus n. This is going to be my first term. Make sense, everyone? Okay, now I'm expanding my second term. Again, it's going to be NA. So I have NA times log NA, but because I have a minus sign here, so this minus is going to become plus. Does that make sense to everyone? Okay, so I do the same for the NB. Okay, again, you get this. Okay, so now we begin to see some interesting pattern emerging. So first thing is that we see this NA plus NB equals N, right? But they have different sign. So these three terms cancels one another. Okay, does this make sense to everyone? Okay, so these three terms cancels one another, and we only have the three log terms remaining. But this is n, right? And we know that we can split n as na plus nb, right? And if we do that, we can group the na terms together and group the nb terms together. Okay, so this is what we have. Okay, so now when I group the term together, I put this na, basically I have minus na times log na plus, right? And I take the sign out. So within the log, I have na over n, and for the same reason, I have nb over n. Does this make sense to everyone? I just want to make sure this is clear. Okay, so now what is, now if let me ask you this question, what is na over n and what is nb over n?
Xc and Xp.
Mole
XP.
fraction.
This is the molar fraction for the A atom and the molar fraction for the B atom, right?
Yeah.
That makes sense to everyone. So, and this is good because, we derive this for 1 mole of system, but eventually want to write this in terms of molar fraction because we want to apply what we derive here to also, applicable to other molar fractions because, in the experiments, you rarely work with 1 mole, exactly 1 mole of system. So writing them in the molar fraction is very convenient, right? So now what I do is that, within the parentheses, we already see clearly that Na over N going to be my XA, which is the molar fraction, NB over N going to be XB molar fraction. Now what I do is that I divide the whole equation by minus N. So I can take this out where N is the Avogadro number, right? I take this minus N out. And then if you focus on this, I take a minus N out. What I left behind is going to be Na over N. Exactly the same as in here. So I have an XA in front of this. Does that make sense to everyone? Okay, and for the same reason, I have, because I take minus n out, so in here I have nb over n, which give me xb. And because this is a negative sign, this is a negative sign, I take the negative sign out, so I have a plus. Does this make sense to everyone? Okay, so this is our key results. But don't forget, what we're trying to do here, we're not trying to do the math, we're trying to find out the entropy of mixing, and in this particular case, the entropy for my mixing state, right? So I have to plug this back into my expression for the entropy. We almost get there. The only thing we're missing is K, right? So when we plug this back in here, I hope I have expression for you. I do. So this is going to be minus k times n. And within the parentheses, we see a very, very elegant symmetric expression, xa times logarithm xa plus xb times logarithm xb. Okay, so now if we think about what is this number, k is the Boltzmann factor and n is Avogadro number, right? So if you introducing the gas constant, I think it's not really introducing, but it's by definition, this is a gas constant. But anyway, so let's further simplify the expression by using the gas constant. Okay, by writing k equals to a or n here. Now my entropy is simply this, right? Minus r. R is the gas constant. The value is 8.31, I guess, and xa times log a plus xb times xb times log xb. Okay, so that is my expression for the entropy. Does this make sense to everyone? The derivation is clear?
Yeah.
Good. So now my question for you is that if you look at this expression, do you see anything that seems, a little weird, or you're totally okay with this? I understand this question makes more sense if I show the derivation on the blackboard, because if I do this in person, there's some probability that I made something wrong during the derivation. So this question makes more sense. But for now, you know it's correct.
Cannot be negative.
I'm sorry, what's that?
Entropy cannot be negative.
Entropy cannot be negative, exactly. So does this negative sign annoy you or at some point? Because when I first saw the expression, the first question I asked, did I make something wrong? Because I do not expect to see a negative sign here.
Yeah,
right?
but in the logarithmic term, it's
Mole fraction is less than 1.
It's less than
So-
1, so we are going to get the log term negative. So I think that negative is going to be cancelled out.
Exactly. So that's the point, right? So again, this is a general way that, when you derive something, do not just accept, what you have done is definitely correct. And, go back, re-examine, look at it and trying to rationale, is there anything wrong with it? Does this mathematical form looks reasonable? Things like that. This is kind of a general way that I think will be very helpful. Okay, so yes, that's the point I'm making. So this, in general, because when we look at the entropy, right, we know that you definitely have a lot of states or configurations. So we know the entropy should be definitely positive in this case, but nonetheless, we get a negative sign. So, the first thing I check is that this negative sign reasonable? And then after I see this, okay, the answer is yes, right? Because XA is what? It's a molar fraction. And we have emphasized several times that this thing is between 0 and 1. Right? And if you take a number smaller than 1 in the logarithm, the whole thing gonna be negative, right? And the same for this part. So you have, within the parentheses, a negative number, and then you have a negative sign. So altogether, this entropy is positive. Okay, so does that make sense to everyone?
Yeah.
Okay, good. So I know there's someone giving me a lot of comments, but because I have to keep the flow going, so I'll address the comments, I think, at the end of the lecture. Okay, so that's that. So now this we have expression for the entropy, right? So let's take some closer look at this entropy. Okay, already give you the entropy of mixing, but that's the same because the entropy for the first state is 0. Okay, so now again, so the whole we did a very a nice derivation for this cool expression, but don't forget that what we're trying to do here is to get the entropy of mixing. So by definition, that is basically you take the entropy for the solution state minus the entropy of the this ordered phase separate state, but that entropy is 0. So basically the entropy of mixing is simply the entropy of the solution state, which we just derived, right? Now, if we take a closer look at what is the mathematical form of this, or no, what is the a function of this entropy as a function of one of the molar fraction, because it looks like that this entropy is a function of 2 variables, but I claim that it's only 1 independent variable, right? Can you tell me why that's the case? It looks like the entropy is a function of both XA and XB, but I told you that only one of them is independent.
XA plus XB equal to 1.
Because XA plus XB equals to 1, right? This is a molar fraction, and we only have 2 type of atoms. So we know that the molar fraction of A plus the molar fraction of B have to equals to 1, right? So only one of them is independent. So that is basically, you can plot the entropy of mixing as a function of one of the molar fractions. You can either choose A or B, doesn't really matter, but you have this. Okay, and you can see several features. I think I highlight some of these for you. The first one is that, okay, so the first is you can see that as long as you move from 0, okay, which means that you start mixing the two atoms, you get an increase of entropy. Does this make sense to everyone?
Yeah.
Yes, right? Because the mixing state is always going to be more entropically favored because you're introducing more states, right? You add more randomness. So this definitely makes sense, right? And then as you add more, in this case, is the molar fraction of B, right? So when molar fraction of B equals 0, what do we have as the starting point? What do we have here?
The
All
pure
A.
This is a pure A, right? This is a
Yeah.
pure A. So now, so if we follow the curve by increasing the molar fraction of B, this means that, okay, we start from a pure A, and we start to throw some B atoms in A and allow them to form a solid solution. Does that make sense to everyone? So we just, initially we just dissolve a very small amount of B in A. Okay, that's what we start, okay? And you can see that initially the entropy increased very quickly and then they start to bend over, okay? And why is that? Why is increase initially very fast and then start to bend over? Any intuitive thoughts? Okay, that might be a difficult question. So the reason is that initially when you add a little bit amount of B, so basically what does this information tells you? The bend over tells you the slope is getting smaller, right? The increase of entropy is getting smaller. But entropy is a increasing function of number of states, right? Of different configurations. So if the entropy grows slower, this means that the number of states, the increase of states as more B is added, going to grow slower, which means that initially, if you just add a little amount of B, you get a huge increase of number of different states, right? Which you didn't have before because initially you just have one state. So you just add a little amount of B, you get a huge increase of number of states available. But as you more and more add more and more in B, the number of increase for the available states become less and less. That makes sense to everyone? Okay. So now eventually you get to this point. Okay. Now you can do this rigorously and find out, let me ask you this. Okay. If I want to ask you, find out what is the molar fraction for the highest point of the entropy of mixing based on this expression I give you, how would you do that? What is the mathematical procedure you find out the largest, the fraction associated, molar fraction associated with the largest entropy of mixing?
You
It's
take,
0.5.
you take the derivative.
Derivative of
The
it.
slope will be 0 at the maximum.
Exactly. So first you write down XA equals to 1 minus XB. So you convert everything as a function of XB, right? And then you take the derivative of the whole expression. Okay, and I already showed you the curve, but so there are only one local maximum or local minimum or local optimum associated with this guy. So at that particular point, the slope goes to 0, which means that the derivative of this entropy of mixing with respect to XB equals to 0. And from there, you can solve XB equals 0.5. Okay, I will leave this as exercise for
I
you.
have a question.
Yes.
Can't we generalize, like if we have like equal composition of the two atoms or more atoms, so at the equal mole fractions of every type of atom, we have the highest entropy at any time, always?
For the two atoms, I can tell you this is definitely the case, but for more, I'm not sure. I haven't worked out the details, but I would imagine that the maximum entropy of mixing would always be achieved at the equimolar fraction case. I would assume, but I didn't work out the details, so don't take my answer for
We
granted.
can just divide one by the number of components that we are having in the system, rather be easier.
We could. I think the easiest way is to generalize this, right? Because you have 3 atoms and you can do the same thing. So that's what I assume, that mathematics could look very similar, but I didn't work out this. So I would say due to the symmetry of the problem, so it very likely that is the case, and which is quite intuitive. But again, I cannot prove that for you right now. But you can definitely work it out. Okay, that's a good point. Yeah, thank you. So that's that. Okay, so this is the maximum. And then if you further increase, so the interesting thing is that, okay, this mathematics tells us that, you know, if you have equal molar fraction of A and B in this case, you reach the maximum entropy of mixing. But why you get a decrease if you further increase XB? How do you, you know, rationale this?
Oh, it's because you're taking away atoms, right? As you increase the amount of B, you're taking away A.
Yes. So the thing is that, you know, if you start with 0B and begin to add B in A, this is going to give you an increase of states, right? But if you, you know, pass the 0.5 point, okay, and keep on increasing, this means what? This means that effectively you're dissolving A, start dissolving A in B, right? So it's the same thing. To look at this is that you reach, for example, if my point reach here, you know, you can consider from this pathway. So you're dissolving A in B, or because you have so many B atoms, this is going to limit the how differently A can pack on different positions. So this is going to reduce the number of available states. Okay, that's why you get a decrease of entropy. But as I said, you can equivalently understood this by looking at this end. Okay, when when xb equals to 1, you start with a pure B and you begin to add a small amount of A in B. So you get the same, exactly the curve, you know, symmetric about this part. Okay. So that's the entropy of mixing. Does this make sense to everyone?
Yes, sir. I have a question again here. So if in this case the entropy is decreasing, so how because the entropy of the universe can never decrease, like it goes on increasing. So how can we account for this kind of situation, like where the increase in the entropy of the overall system plus surrounding is taking place?
So
It
I think
has-
that the first statement you say, well, entropy is always increasing is certainly not true.
of the universe, I mean, system plus surrounding. So
I'm sorry?
uh,
So this is entropy of mixing, right? So it's initially, so the reason why you say it's decreasing is because you choose to look at the entropy as a sole function of XB,
yeah.
right? So we're looking at the entropy as a function of XB, and there's no reason why entropy cannot decrease if you increase XB. I don't think there any reason to believe entropy has to always increasing with increasing XB, right?
So I think then the later process, like from the first half, from the half, so it might not be like energetically favored. So if we add more heat to the system, then probably the
You add more atom to the system, but you limit the different ways how they can pack, right?
yeah.
So
Okay.
the key is to understand, because the contribution of the entropy comes to how many different ways you can pack these A and B atoms. You add more B atoms over a critical concentration, which is 0.5, you leads to a limited number, a smaller number of ways how you can pack them. So this is going to lead to a decrease of entropy. I don't think there are any contradictions here, right?
Okay.
Okay, so okay, that's the entropy. I think yes, I think this is I'm you know kind of being slow here, but I guess it's good for us to understand because it's a very important concept that will be used a lot again. So yes, and this is also the mechanism for high entropy alloy. It's just so for the high entropy alloy, why, you know, what is high entropy alloy? You know, traditional alloy only add a little bit, you know, A and B. The high entropy alloy is that you first have a multiple you know, species, typically 5 or more, right? And you mix them with almost equal molar fraction. And we know for a matter of fact that, you know, based on this two component system, that, you know, if you mix a large number of different atoms with almost equal molar fraction, you're going to definitely achieve a very high entropy state. So that's why it's called a high entropy alloy. Okay, now we're not talking about this is a kind of new material system, kind of interesting, but we're not going to spend too much time on this. I'm just going to show you that, you know, the very fundamental things, the very simple models that we study in the class is also can provide insights to really understand more complex systems that people are studying. Okay, so now let's enter. So this is entropy of mixing, but don't forget our role is to go back to find out the free energy of mixing, right? And for the free energy of mixing, do you remember how it's related to the entropy of mixing? Delta G mix equals to what? Minus T times delta X mix, right? So you have a minus T here because delta X mix has a minus sign here, and we know this guy is always positive, but you have a minus sign in front of this and times T, so this is going to be RT, and there's no minus sign anymore, and then you have in this. Okay, so the first question for you is that what's going to be the sign of delta G mix?
Negative.
It's going to be negative, right? And except for the two trivial points when xa equals to 1 or xb equals to 1, right? Except for these two trivial points, my delta G mix is always going to be smaller than 0. Does this make sense?
Yeah.
Except for the two trivial case that xa equals to 1 and xb equals to 1, my delta G mix is going to always be negative. Does this make sense? Or is
Is
this
the
rigorous?
enthalpy of mixing also 0?
Yes, the entropy of mixing for those extremes is 0, right? So except for these 2 points, my delta G mix is always going to be negative. That this correct?
Yeah, according to
Okay.
equation, it
Yes.
seems.
Okay, let me say this again. Okay, so except for the trivial case, xa equals to 1 or xb equals to 1, namely have pure A or pure B, the entropy of mixing can always be positive. Is this correct?
No.
This is
Practically not, but according to equation.
okay. So I think I'm not tricking you here. I'm just trying to you know, how to say this, you know, trying to, you know, bring a very important factor here. Okay, so let me say this again. If you look at the entropy of mixing, right? My claim is that except for the trivial point that x equals to 1 and xb equals to 1, where you have pure A or pure B, except for these two trivial points, my entropy of mixing is always greater than 0. Is this correct?
No, this is not.
No, this is not.
Why not? Because we already showed this. Except for the 0 and 1, for these two extreme points, can you point out any other points that entropy of mixing not positive except for these two? That's a correct statement, right?
Okay. The entropy is greater than 0, but the free energy will be negative.
Yes. So my forwarding statement is that, okay, the free energy, except for the trivial point xa equals to 1 or xb equals to 1, the free energy can always be negative. Is this correct?
Yes. This
Yes.
is
Yes.
But sir, I have like a practical example in that case, which is not correct.
No,
Like
there's no practical example. I'm just asking you to staring at these two equations and see what are the difference between the two. There is a difference.
according to
There's a
equation, it seems that
There's a
correct.
temperature term here, so at
It-
negative temperatures.
exactly. There is another factor. Okay, so the difference between entropy and free energy is that there is a factor of temperature that play a role. Okay, although in this system the temperature almost play a trivial role, but it's not exactly. Okay, we don't have negative temperature, we could, but let's say we have normal systems, okay? And what condition, what I said is not true.
But sir, I have a question here. The temperature is on absolute scale, and it can't be even 0. So how
Negative,
can the
yeah.
temperature be?
The temperature cannot be zero, cannot be negative, but it can be 0. When
But
the
the
temperature
absolute
equals to
temperature-
0, when the temperature is equal to 0, you know, the molar fraction does not play any role in here.
Yeah.
That's the point I'm making. So the whole point I'm trying to point here is that we need to recognize that the difference between, so the mathematics of the two are almost the same. Okay, there's one thing we all can recognize, which is the negative sign. But there's another factor which is typically not quite clear or is very easy to be ignored, is the effect of temperature here. Okay, for finite temperature is quite clear, but don't forget, you know, because you have this new factor here, there is a case when t equals 0 and the system are all energetically equally favored. Okay, that's the point I'm making here. So do not take grant for any statement that seems to be correct. Always think more deeply and more critically. Okay, that's the point I'm trying to make here.
In reality, we can't achieve absolute 0 temperature, right, at all.
We're talking about mathematics here, and in principle, you can still achieve that particular state where the free energy of the systems are identical. So this is going to be a trivial state, but I'm trying to make this whole statement mathematically rigorous. That's the point I'm making here.
Okay.
Because we're examining the mathematics. It's good to associate it with your tuition, but the more important thing is to recognize the very subtle differences and the consequence of this difference. That's what I'm making. Because, you know, when you do research, you know, sometimes there's a small factor which is hidden there, but if you just take it for granted, you know, you're going to miss some big discovery. That's the whole point. Okay,
Mm.
so but anyway, so that's almost correct, right? So our intuition is almost correct. There are two distinctions between delta X mix and delta G mix. The first one is that you flip the curve of the free energy of the entropy, right? The entropy gonna go up like this, right? But the free energy gonna be flipped, and it's always gonna be negative. Okay, but you have the same local optimum, okay, achieved at XA equals to XB at 0.5. The role of temperature is the following. Okay, if you have high temperature, you kind of enhance the role of entropy, right? And if you have low temperature, it's fine. You still want this two state to have a negative free energy. But when T goes to 0, okay, you see that the free energy or the entropy of mixing won't gonna play any role here. Okay, so now the question for you is that, okay, for at a given temperature that is greater than 0, okay, for a given temperature that is greater than 0, based on our analysis, which state gonna be more thermodynamically favored, or which state is more stable at a finite temperature, this mixing state or this demixing state?
Mixing state.
Mixing state.
The mixing state is always more favorable for any finite temperature, right? Does this make sense?
Yeah.
This is independent of molar fraction. Doesn't really matter how much A or B you mix together. It doesn't really matter what is the temperature as long as it's not 0, right? And under any finite temperature, it doesn't really matter what is the molar fraction, the mixing state, except for the trivial case you have pure A or pure B. But if we talk about mixing, it's not going to be those two states, right? So the mixing state is always going to be favored compared to the mixing state for any finite temperature. That's our conclusion. Does this make sense to everyone?
Yeah.
So this is for ideal solution, okay? This is for ideal solution. So this means what? What is the key factor determining thermodynamics of ideal solution?
So the atoms are not interacting with each other chemically. Or there's no interaction energy. The delta H is 0.
Yes. So the key factor determining the state of ideal solution is only entropy. So this system is completely determined by entropy. And we know that if we have a mixing state, you're always going to have a higher entropy, right? And because the system is completely determined by entropy, so of course, the mixing state is going to always be more thermally stable or thermally favored at any finite temperature. So, we went through all of this analysis, and you see the conclusion is basically quite intuitive. Okay, so that's what I'm trying to tell you here. So now let's go back to one more step. So this is the free energy of mixing that we all derived together. Okay, this is a very beautiful expression. But now don't forget, the original goal is to find out what is the free energy for this state we call state 1, and what is the free energy for the second state, right? And we already know the free energy for the first state is simply the linear combination of two molar fractions the molar free energy weighted by the molar fraction. And we write down the second state, the free energy of the second state as G1 plus delta G mix. But we went through all the trouble to find out delta G mix, right? So now we're very proud that we can write down the expression for the free energy of my solution or the solid solution state, which is just to plug in this expression for delta G mix right in here, right? That makes sense, everyone? So we have this. And now let's regroup this a little bit, okay? Okay, what G2 looks like, I think I want to show you a plot, but let me show you the plot first. Okay, so this is, so if you look at this plot, okay, this plot shows us what delta G mix looks like at different temperature, right? Does this make sense to everyone? Okay, now what G1 looks like? If I plot G1 as a function of XA or XB, what do you think you're gonna have? Do you have some very complex curve, or do you have a, something like a straight line?
Straight line.
A straight line. Is this straight line gonna be a flat line, or in general it has a slope?
Flat line.
Are you sure it's a flat line?
Yeah, if the atoms are same, then all microstates will be the same.
Okay,
No,
so
it's gonna have a slope.
So what determines the slope?
The composition XA and XB.
No, XA and XB have nothing to do with the slope. It's the variable like X. What determines the slope? What is a constant in this equation?
That gives free energy.
Exactly. So when XA equals to 0, what do we have?
XB plus
XBGB.
But XA equals 0, XB definitely equals to 1. So we have GB, right?
Yeah, GB. So
Okay.
G1 equal to GB.
So GB will be the intersection of that particular curve at XA equals 0, right? Because,
Yeah.
and XA equals to 1, XB equals 0, we have GA. So GA will be the intersection of the curve with the axis when XB equals to 1, 0, right? So this is your curve, this is your slope. So the slope is determined by what? GA minus, or GB minus GA, right? Because this part is always equals to 1 because your fraction only vary from 0 to 1. So you always have 1 here. Now this difference is going to give you the slope by definition, GB minus GA. Does that make sense to everyone? Okay, so that's going to be given by G1. It's a very simple linear curve, but it has a non-zero slope in general, unless you have exactly or identical GA and GB. But anyway, so now, without doing any mathematical calculation, okay, I give you the plot for G1, I give you the plot for G2, and I already showed you here, this is the linear combination of G1 part plus the delta G part. Okay, how would you imagine that my G2 looks like? Okay, so again, I cannot show you this, but literally what you do is that you take this guy, okay? You take this guy, and then you match this point here, and you match this point here. So basically, you know, you take this curve, twist it a little, and glue the curve to this straight line. That's what you get, okay? Does that make sense to everyone? So again, that's a rough way of estimate what G2 looks like. I ask you what this looks like. Okay, that's the easiest way, you know, to graphically demonstrate, you know, a complex function. Okay, that's another trick that I think we're going to use a lot in the subsequent classes. Okay, so that's what G2 looks like. As you can see, okay, adding G1 to delta G mix does not change the rho of temperature, does not change the rho of molar fraction, right? You still have the same conclusion, roughly the same conclusion. The only thing it changed is that it breaks the symmetry. It breaks the symmetry of the curve. Does that make sense to everyone?
Yeah.
Okay, so now what is implication for this? What?
So now the delta G is minimum,
Yes.
like is most minimum at the mole fraction, which is not equal, like XA is not equal to XB.
Exactly. So by breaking the symmetry is because, you know, you have GA and GB not equals to one another. So this is gonna give you a asymmetric local minimum for that particular system, right? Because when GA not equals to GB, this means that if you want to achieve a global minimum energy for the second state, that wouldn't be achieved by the equimolar fraction state. Okay, and in this particular case, when GB is higher than GA, it's going to achieve at a molar fraction for XB smaller than 0.5. Okay, now we're going to talk about that why later, but this is the meaning of broken symmetry. Okay, does that make sense to everyone? Again, you can rigorously write down what is the expression for GB as a function of, the expression for the minimum of XB, for the XB associated with the local minimum of G2 as a function of GA and GB, and you can see why that's the case. Yes, for questions.
What does it mean in a physical sense? Like,
I'm sorry, what was that?
does it mean that the asymmetrical local minimum is moved?
Okay, so this is what I mean a symmetric curve. Okay, so the symmetric curve means that you have you know, but literally if you look at the curve and you can define axis. So if you flip the curve, you know, with respect to axis, the left part is gonna coincide exactly with the right part, right? And we know that this for a symmetric curve, if you have a local minimum, that local minimum has to be achieved at the symmetric axis, because that's the only way you can construct a local minimum for a symmetric curve. But non-symmetric curve.
Does it mean like in a physical sense? What does it mean?
Physical sense means that when you mix A and B, so if you have the same molar fraction of A and B, you achieve a lowest or smallest entropy, free energy of mixing. So if you can vary the molar fraction of A and B, and by varying this molar fraction, you can achieve different stability with respect to the ideal state, okay? And that relative stability is maximized at XA equals to XB equals 0.5, Does that make sense? So this is the physical meaning of delta G mix, right? Delta G mix tells you what is the gain of free energy in terms of stability. And if you basically this particular results, this plot tells us that at XA equals XB equals 0.5, you have maximum, not really maximum, but largest difference of delta G mix, which means that at this particular point, okay, your solution state is most favored compared to the phase separate state. That is physical meaning. Okay, does it make sense? Okay, so I assume so. Okay, but the thing is that in here you see that the delta G mix is achieved, right? If you just look at this difference, this difference can be achieved always at XB equals to 0.5. But the minimum of this curve, if you talk about the absolute minimum of G2, okay, is going to be achieved at a lower fraction than 0.5. Okay, this is what I'm talking about. Okay, again, this is just about describes the observation about the conclusions that we can get about these. Okay, so I'll stay behind the lecture. You can ask any more questions you want. Okay, but I think I have to move on. So this is the kind of intuitive understanding of the free energy. Okay, but the thing is that we know that for the mixing state, for the demixing state, you can write the free energy in a very elegant form, right? You have Ga, which is the molar free energy for pure A, and Gb, which is the molar free energy for pure B, and you can easily take a linear combination of these two free energy. You have G1. So I'm thinking whether we could do the similar things, right? Because you see we have XA here. How about we group the terms have XAs and the groups the terms have XBs and write the free energy for my second system for this mixing state in a similar fashion as a linear combination of something, okay? So that makes sense. This is my logic, okay? So if we do that, okay, we have this expression, okay? So I group the terms that have XA in front of it, I group the terms that have XB in front of it, and I have these two terms, what I call mu A and mu B, okay? So what is mu A and mu B? It's given by this, okay? So it has this GA and also have this part that you coupled with the logarithm of XA, and you have mu B, which is the same thing, okay? So for those of you who have taken thermodynamics, okay, do you know what typically what we call mu A and mu B?
Chemical potential.
This is what we call the chemical potential, right? Does that make sense to everyone? But what is the physical meaning of chemical potential? Okay, so that's what I'm trying to get here. So, and to understand the meaning of chemical potential, let's compare this mixing state to this, demixing state. We know that, the chemical potential, the rho of chemical potential is similar to the rho of G and Gb, right, in the system. Okay, we know Ga is the molar free energy of A atoms in the pure substance, right? So that you can simply write down the overall free energy as a linear combination of the molar free energy for A and B, because you have this mole of A, you have this mole of B. So you take the molar fraction and you take the molar free energy of A and B, and that's going to give you the total free energy, right? That's going to be the insight for G1. So now if we follow the same line of thinking, what's going to be the chemical potential? Okay, if we follow the same line of thinking, we see that the meaning of chemical potential is similar, right? It can be considered as the molar free energy of A and B atom, not in a pure state, but in a mixing state, right? Because, I tell you that I mix this XA mole of A and XB mole of B, and I get a free energy of G. And you write the expression that the G equals to XA times mu A plus XB times mu B. So naturally, mu A and mu B are the molar free energy of A or B atoms. It's not in this mixing state, not in the pure state. Does this make sense to everyone? Okay. So that's the physical kind of, based at least from our analysis in this particular context, a very, very nice way of understanding chemical potential. It's just a molar free energy of a particular atom or element, but it's not a molar free energy in a pure state. It's a molar free energy in a mixing state. Okay, so now I'm running out of my time, but I just want to quickly point out some very interesting facts, and we're going to pick up those from the next lecture. Now, if you look at mu A and mu B and see how it compared to G and Gb, let's focus on mu A. Is mu A in terms of number greater or lower than Ga?
It's it depends. Like
Suppose we have finite temperature.
Would it be
is,
It's
great?
lower.
less
No,
than
it's
T is
lower.
great.
less than
T is greater than 0. We have finite temperature. Okay.
less than
Lower.
zero.
It's limit definitely always lower, right? Except for the trivial case when xa equals 0 or xb equals 0, right? And in those cases that make quite sense because you can well list the logarithm. But anyway, so this part is positive, right? And if you look at xa in a normal range, it means that greater than 0, smaller than 1. This can always be a negative number, right? So if you compare mu a and ga, what is the conclusion? Mu a is always going to be lower than ga.
Yes.
Right? This is the conclusion. That this makes sense? What does this mean? This means that, okay, my molar free energy, for if you look at A, right? So the molar free energy of A in the mixing state is lower than the molar free energy of A in the phase separate state or in the pure state.
Yeah.
Does this make sense? That this
Yes.
consistent with conclusion?
Yes.
Right? Because why? Because this, what does this mean? This means that they're happy, right? You're making them in the mixing state. You lower their chemical potential, so they're happy. So they favor the mixing state, which is the same conclusion that we get from the free energy analysis. Does this make sense to everyone?
Yes.
Okay, so good. So I'll stop here for the lecture. And yes, and we will pick up from the chemical potential part in our next lecture, which will be on next Tuesday. Okay, so thank you so much. So I'll see you next Tuesday. Let me stop recording.